没有老师的话可以，当然就这个是他读的，就是他我们读这种说 peer presentation。哦，你在这个对，他读30秒。我讲如果你要走这个因为我们下一个 short sem 没有教书，就不能对，那下一个不能去我们这个哪些不一样？因为我下一个 short sem 没有教书，对比较。我等下办法，你先找一些资料来看看什么比较有趣的，然后不懂的，然后可以。先是肯定的跟上。Hello. Right. Good morning to everyone. I got few requests from some of you. Let's start from Jiaye's balloon. So Jia, please
listen, and then if you have any question, you can. If you have any question, you just follow up on the spot. It's okay. Yeah. Okay. So basically, Charlie asked about. So let's spend this hour doing some tutorial. Okay, tutorial for the assignment. Assignment 12. Okay. So Jay asked about how to understand the mapping property of the free group and quotient group, right? Okay. So let's look at some examples of mapping property of free groups or quotient group. If you are not familiar with these terms, please take out your definition or the proposition for these two mapping properties. Okay, please bring your definition or proposition beside you. All right, so let's look at the first example. Okay, first let's look at the free group generated by one object. Free group generated by A. Okay. Anyone recall what the free group is? Free group generated by A means? So in particular, this is the equivalent classes of word. Equivalent classes of word. Okay, what does this mean? Here. Okay, so what are the elements in here? Right, what are the elements here? So equivalent classes means they are set. Okay, they are set. So the elements here are, for example, the identity. Okay, so what are in the set of identity here? For example, identity, right? And the word A concatenate with A inverse concatenate with A inverse, right? And then maybe A inverse, and so on. So these are the words that can be cancelled, okay, when they are side by side. Okay. And so you have inverses here. You also have identity. So what's the identity? The identity is the empty word. Okay. And what's the law of composition? Well, we should talk about law of composition. So the law of composition is just the word concatenation, or the word juxtaposition. So you just put words side by side, or letters side by side. Okay. So this is a free group. Let's say we want to map free group. Okay, map from a free group. What do you need to do? Okay, so let's say we want to map the free group generated by A to a group, say Z. Okay, say Z. So two of these are groups. On the right hand side is Z. I guess Z is a group under addition. Okay, and then left hand side is also a group. Just now I described for you, this is a free group, which are the equivalent classes of word. So I define like this homomorphism here. So I send A to 1. Okay. So how about if I send A to A, how about AA? Where should AA get sent to? Well, this AA should be something called phi AA, right? Okay, what does this phi AA should equal to? Phi A times phi A. Okay, so this means that I actually naturally extend the map. I can always do this. Okay, I naturally extend the map of set. Okay, so I can set it by, I define it to be phi A times phi A. Okay, but this multiplication here is in Z, so it becomes a plus. Because the codomain of phi is Z. Okay, so since I know where A should go to, then phi A plus phi A is 1 plus 1, which is 2. So A squared is going to 2. Okay, no? So this is the this is what mapping D of free groups tells you. So there's no checking of homomorphism that you need to do. Okay, it naturally extends if you define on generators. Okay, A is your generators here. So you need to define maps on generators. Defining map on generators. Extend defining. Extend to a homomorphism. Extend to defining a homomorphism. Okay. So this is what good about these three good things. Because if you just define map on generators, it will naturally extend to a homomorphism. Does it make sense? Okay. So you naturally extend it. Okay. And actually, what's the kernel of this map here? So what's the kernel of phi? When does A get sent to 0 in Z? What's the kernel of phi here? What's the thing get sent to 0 in integer? Sorry? Just identity, okay? Because 1 can never go back to 0, okay, in Z. Only identity gets sent to 0, okay? Identity in the free group. Does that make sense? Okay. So meaning what? This homomorphism is bijective so fast. Just injective, right? Okay. So is it surjective or not? Is this map surjective? Can you write every element? Can you find every pre-image for the element in Z or not? Yes or no? Why? Z is a cyclic group. You prove in the exam, right? In particular, it is generated by 1. So I know the pre-image of 1. What's the pre-image of n? A about n, right? Okay. So also, P is surjective because P of A to the power n is equals to n for all n in Z. Okay. So you have a bijective homomorphism, meaning you have what? You have a bijective homomorphism, meaning you have a isomorphism. Okay, so meaning that is isomorphic to free group generated by one element. Okay. Okay. Or more frequently, we will write Z equals to A. Okay. We write Z equals to A. And what is this A? Actually, this A is what? I don't know. Okay. So we really don't differentiate between one and an element. Okay. A letter. Okay. Okay or not? Okay. Or there's the second method which you can use first isomorphism to deduce. Deduce Z equals to A. So how do I use it? So similarly, we have a free group mapping into Z, okay, using a surjective homomorphism. What's the surjective homomorphism? Sending A to 1, okay? And then just now we check that the kernel, okay, the kernel of phi is the identity generated by the identity. Okay, so meaning what? So meaning if I take the free group, okay, I quotient out by this trivial subgroup, what do I have? I have first of all, I have a canonical map from A to S/E. Okay, the canonical map, we call it pi. Sends every element to it coset. And then there exists a isomorphism here. Okay, there exists an isomorphism here. Okay. But what is A quotient by the trivial subgroup? What is A quotient by the trivial subgroup? What is A quotient by the trivial subgroup? What are you killing here? You are just killing the identity. So not that the free group quotient out by the trivial subgroup is really just the free group. Sense? That makes sense. Any question? Yep. Sorry. Which quotient group? This? No. This is a free group generated by one element. So there are infinitely many words here. All the words, equivalent classes of words. How to understand this isomorphism here? Build the surjective homomorphism. from the free group A to free group A. Easy, right? Just send A to A. What's the kernel of this map? The trivial subgroup. Okay. Then by first isomorphism theorem, it gives you the isomorphism. So how do you differentiate these two groups? Actually, it's very important. You need to imagine what's the element inside here. Okay, how you represent them is very important here. Because in rings, we will see it again, quotient ring. Okay, so how to see these element, how to see the set here. On the right-hand side is a free group generated by one element. So this side is easy. Can you give some example of word? Ishan? Let's give some word on the free group generated by one element. Sorry? CAN. There's no C here, there's no N here. There's only A here. A, no? Right. Can someone give other word or not? Grace? What word you can give here? Free group generated by A. 2A? There's no 2A here. You can only concatenate A few times. A squared. Okay, A squared. Possible. How about others? Let's check. You give some word here other than these two. A cube. Right, sure. Why no one give identity one? This is a very important word here. Or the empty word. Okay, this one is very important word here because it's the identity. Okay. So I said there's a isomorphism, right? So how I represent this guy in this quotient group? How should I write it down? Anyone have any idea? No? Quotient group by definition is what? In sense. By definition, what is quotient group? Very important. This concept will carry on to rings. Okay, so what's the definition of quotient group? Set of coset. Okay, so you should write elements in the left-hand side as cosets. Okay, so what are the cosets here? Coset is what? A times some subgroup. Okay. So what's the obvious subgroup in this coset here? It's the trivial subgroup. Okay, this is your H, if you like. Okay, what are the other coset here? Corresponding to the word given by your classmate. A times the trivial subgroup, A squared times the trivial subgroup, A cubed times the trivial subgroup. Okay, or just the trivial subgroup. I write it down already. So these are the four correspondent elements. Does it make sense? So there's some subtlety here, okay, but they behave the same. That's why we say isomorphism. Make sense? Okay. So A times trivial subgroup correspond to A under this isomorphism. A squared times the trivial subgroup correspond to the A squared element on the other side, and then A cubed H correspond to A cubed, and H correspond to the empty. Okay or not? Please understand these examples. It's very important for you to read the proposition. Okay? Make sense? Jia, is it okay? Clearer? Okay. How about I let you all try this example here. Try spend about 3 minutes to prove this. That a free group generated by an element Z quotient by the Z to the power n relation. This is actually isomorphic to Z n. Try and prove this. Try and construct the surjective map and then try and find a kernel and then use first isomorphism theorem to deduce this. So the most crucial thing to find this isomorphism is to construct a map, a surjective map, okay, or directly construct the isomorphism. Okay, so that constructing map becomes very important, very crucial here. So later on, my find new alarm. Okay, is it almost done? So what's the map you have? Let's say Zhengcheng. Have you tried anything? No, you didn't try. You try. Sorry, you tried. Can you tell us what did you try? You can't. Okay. Uh, let's get someone else. Ryan, did you try anything? Right? What did you write down? You write down anything yet? Z to the power n. Yeah. Z to the power n. Yeah. What's the meaning? Do you mean what's the meaning of this presentation here? Okay. So let's discuss this. So what's the meaning of this presentation? So this is what we call the presentation by generators and relations. Okay, so what are the generators and relations here? So before the left-hand side of this bar here is what we call the generators. On the right-hand side of the bar here is what we call the relations. Then you need to say what's generators and relation do. Okay. So in this definition here, generators will generate a free group. Okay, meaning I use the generator to make out all the words. Okay, you can do A inverse A cancellation here. Okay, so it forms a equivalence classes. What are the relations? Relations are words. Okay, that evaluate to the identity in the presentation. Yeah. Which one? What are you asking? Equivalence. Oh, you mean? Okay, let me finish this. Let me finish this. Okay. So the relations are word. Okay. Are words that evaluate to the identity the group defined by the presentation. Okay. So what's the group? So meaning, okay, let's keep like this first. And then from this two, okay, so what's the presentation by generators and relation? So presentation by generators and relation is a quotient group where the free group generated by the generators is quotient by the smallest normal subgroup generated by the relations. Okay. Let's give you an example how to read this Z slash mod Zn here. So how does this definition translate to doing computation, right? Okay, how does it translate? Okay, listen carefully. How does this translate? So inside here, what words are in here? Okay, we have free group generated by Z. So for example, we have Z, Z square, Z n Zn plus 2, Z2n, right? I can only concatenate Z. I only have letter Z. Z to the 101n, right? But I say that Zn here have to be evaluated to identity in this group here. Okay, what happened? So there's implication on the multiple of n. Okay, for example, Z to the n here is equivalent to identity. Z to the n plus 1 here is Z to the 2. Z to the 2n here become identity as well. And Z to the 101n go to identity as well. Okay, what are the identity here? These are the empty word. Okay, now. So this becomes smaller than the free group already. So how many non-trivial elements inside here? How many? N is just n of them, right? Identity Z to the 0, Z to the 1, Z to the 2, up to Z to the n minus 1. Because Zn, you go back to identity again. Okay. Does it make sense? Okay or not? Yeah. So why is there a subgroup word? There's a normal subgroup popping up here. So if you consider Z, Zn, Z minus 1, what does this word evaluate to? Sorry, means you? Zn. Zn is evaluated to identity, right? And Z inverse will cancel out, right? So you get identity again. So meaning what? Actually, conjugation of word should appear inside your relation. Any word, it holds true. Does it make sense? So once you sense the word to identity, all the conjugation will automatically get sent to identity as well. Does it make sense? Okay, so that's why we consider the quotient by the smallest normal subgroup. So what's the definition of normal subgroup? Anyone can recall now? A subgroup N is normal if, so for every element, so a subgroup N is normal in a group G if for every element in G, G and G inverse is a subset of N. So it contains all the conjugate. And this is what we need for this quotient here. If I send a word to identity, then I'll send all the conjugate of that word go to identity as well. Make sense? Does it make sense? Okay. Okay. So we have better understand of this presentation by generators and relations. So what's the map here? So what should be the injective map here to describe the isomorphism? What's the map here? I need to send Z to 1 mod n. Okay. I need to send Z to 1 mod n. So what's the kernel of 1? So what's the things that evaluate to 0 in Zn? What's the things that evaluate to 0 in Zn? Or evaluate to 0 in Zn? Multiple of n. So like 0 mod n mod n, 2n mod n, minus n mod n, right? these are the things get sent to 0. So in that case, what is the kernel of this phi? What's the kernel of the phi? Z to the n. Okay, so this is the kernel of the phi, or the group generated by Zn, the normal subgroup. Okay, so this is the smallest normal subgroup generated by Zn. Sorry that we don't have extra notation for normal subgroup generated by Zn. Okay, we just have group generated by Zn, so we'll use the same notation. So please don't confuse. So by this, what can we do? We can use what? So we know the kernel of this homomorphism. What can we form? We can form the quotient. We can form the quotient group. Okay. So by first isomorphism theorem, we have a isomorphism, okay, between this quotient group and the image of phi. Okay, and then what's the map that map this diagram commute? This is the canonical map pi. Okay. Does it make sense? Yes.
All the we conjugate all the relation.
Yeah.
Then actually we will get every element that gets.
Yeah. So
Is correct. If we conjugate all the normal subgroup.
Yes.
Then actually this normal subgroup is everything. It's the exactly equivalent class of group.
Yes. 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 Yeah. So what's the equivalent class of 0 in here? So these are Zn, Zn, Z inverse, and Z square, Zn, Z to the -2, and so on. Yeah. And then this 0 here, this 0 coset here under this isomorphism will be sent to the 0 mod n. Yeah, no? That makes sense? So meaning we send the coset to its representative. Okay. If you don't understand, please stare long enough on these examples. Stare at it. Because these are new things. New things you need to spend time with it. Right. You found a new friend, you also need to spend time with them, right? You found a new boyfriend, girlfriend, also need to spend time talking to them, right? So you need to spend time. You cannot say, I teach you, you should have no. Impossible. This is impossible, please. Okay. You need to spend time with them. Don't be too naive. Make sense or not? Okay, any question about showing the isomorphism from presentation by generators and relation? Is it clear now, Jia? What you need to do? Okay, next, I want to address what whying problems here. So, how to understand? So the second question is, how do we really see? How do we see free groups? Too abstract. So I want to bring down to the earth for you. Let's make it really concrete. What is free group? Okay. I don't think this you can see in textbook. So make sure you listen. So what is free groups? So let's take the example of S3. Okay, we have discussed S3 a few times, and then I asked you to do it in assignment. Okay, let's take the example of S3. The presentation of S3. So let's take the free group generated by XY, portion out by X squared equals to identity, Y squared equals to Y cube equals to identity, and then YX equals to XY squared. How do you understand this group here? In the class, I use cardinality argument to reduce the element in this group here. So I can reduce everything to 6-element set. Still remember what's the 6-element set here? E, X, Y, Y squared, XY, XY squared. Why? Because if you go higher order, it will be get killed by these two relations here. If you consider all the YX, YX or YYX, through the third relation here, you can push all the X forward. Once you group X and Y together, you can cancel the higher power using the first two relations. So you're left with this two, this 6 here. Make sense? And then how we really understand this in S3, we need to pick an isomorphism. So remember what's the isomorphism I picked between S3 here? How I realize this as a function composition. What do I pick for S? What do I pick for Y? What do I pick for X? What do I pick for Y? X I pick 1, 2. Y I pick 1, 2, 3. Okay. So these are the words 1, 2, and 1, 2, 3. So I can concatenate words. I don't care how it multiply in function. I can concatenate words. So in free groups, the presentation here, I have 1, 2 square to identity. I have, or to make it really precise, I write empty word here to differentiate between function composition and word concatenation. Y cube, 1, 2, 3, cube to the empty word. Okay. If I do 1, 2, 3, do 1, 2, is the same as doing 1, 2 on 1, 2, 3 square. Cube on square. Oh, this one is cube. Thank you. Okay. And if I use this word, this corresponds to 6 elements here. What are the 6 elements here? 1, 2, identity, 1, 2, 1, 2, 3, 1, 2, 3 square, 1, 2 times 1, 2, 3, 1, 2 times 1, 2, 3 square. Okay, but this 6 element here, how to compose them? I really know them as what? I really know this guy as S3. I know how to compose them in S3. So this is permutation of 3 indices. I can compute them. What is this 6 element here? E, 1, 2, 1, 2, 3, 1, 3, 2, 2, 3, and you should guess this is 1, 3, and then compute it. Okay. 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 So what's this map on the top here? What's this map here? Let's say I call it phi. Okay, what's this phi map here? I'm sending code set to this 6 element here. So what should be the map? So that I have an isomorphism across as well. What's this map? I send all the code set to this 6 element. What should I do? I send the 6 code set to the 6 representative on the right hand side. Okay, so let's write something down here. So what is in the code set of one, for example, code set of the identity or the empty word? So what's the thing inside the code set here? So let's write identity bar for the code set. It's like how you learn the equivalent class for Zn. 1 bar, 0 bar, 2 bar. Okay. So what is inside here? These are precisely all the word. For example, 1, 2 square, 1, 2, 3 cube, and then y square, yx, xy square can be rewritten as yx, yx, right? Do you remember? We can rewrite this relation as yx, yx. Okay. So yx, yx is the word in identity. So in particular, y 1, 2, 3, 1, 2, 1, 2, 3, 1, 2 is in here. Okay. And then what? And then all the conjugation. Okay, you can take all the conjugation. All the conjugation. And so on. Okay. All the composition, because it is closed. Okay. If you take one word composed to identity, take the other word composed to identity, that evaluate to identity. If you take the product of these two, they still evaluate to identity. So they form a group. So N form a group. And then all the conjugation also get sent to identity. So the conjugation of this word is still in the group. Sense or not? Okay. For example, what is in the code set of 1, 2? Michelle, do you know what's the code set of 1, 2? Michelle, do you know what's in the code set of 1, 2 here? What are the things that equivalent to 1, 2? Identity. Identity is not in 1, 2, right? Because equivalent class partition the set. So identity already has one coset it belongs to. It cannot belong to two cosets here. Okay. So if I say I want to find the representative for 1, 2, 1, 2 definitely stay inside the coset. What else? Answer yet. What else is in this coset here? Any idea? No idea. Ziqian, what else is in this coset here? Coset of 1, 2. Give me a specific one. You guys are split, the level split very far. Some complete don't know, some know too much. So you guys are not coherent, this class. Very sparse, the level. Okay, pick one example. 1, 2 times. 1, 2 times 1, 2, 3. No, this is not in this concept. Not either. Sorry. 1, 2, 3 cube. Okay, meaning what? I take the representative, multiply everything in my normal subgroup here. Make sense or not? A times H ma, right? You take the representative times everything in your subgroup, A times H. Okay, right? And also 1, 2 times 1, 2, 3 times 1, 2 square times 1, 2, 3 square, and so on. Okay. And then under the map, guys sends to where? Empty word gets sent to the identity. 1, 2 bar gets sent to the 1, 2. Try and evaluate all the product on the right hand side. What do you give? What do you get if you stay in S3? Huh? If you stay in S3, what is 1, 2 squared? 1, 2 composed with 1, 2. If you are in S3, 1, 2, you compose 2 transposition together. What do you get? Identity. 1, 2, 3 cube, you get identity. And then this, you compose together what? These 3 together, you get what? A bit complicated. Let's compute it. Okay, so let's do this computation. So let's say we stay in S3 now. What happened in S3? 1, 2, 3, 1, 2, 1, 2, 3, 1, 2. What is this? This is 1, 2, 2, 3, 1, 2, 1, 2, 2, 3, 1, 2. Is everyone agree? Agree with this? Agree? Okay. So what is this computation here? The middle 2 cancel. And then 2, 3 cancel again. 1, 2 cancel again. You get identity. So what's this free group doing actually? It groups all the product that evaluate to the 6 element into equivalence classes. So you can imagine these are all the questions you can get, all the type of products you can get in S3. And then the right hand side here tells you there are only 6 kind of answer you can get when you compute products in S3. This is like a primary question. Asks you evaluate the product. And then the only 6 answer you can get is here, on the top here. Okay, there's only 6 of these answers you can get. You cannot get other 6, right? Make sense or not? If I explain up to here, you still cannot see the beauty. Please understand again. Yeah. Sorry. What is also isomorphic?
A more formal way to understand this thing.
A more what?
More
formal. A more formal way to.
is equivalent to G.
What is form? Okay. So you say.
I just doing the that is equivalent to E. By doing the
yeah, sure. So we are understanding the computation, the equal using map. We use map to understand here. We use the map. We use map. So we know that 1, 2 times 1, 2 is the identity. 1, 2, 3 times 1, 2, 3 times 1, 2, 3, which is also identity. So all these get equal to identity. So we form a map. Okay. Does it make sense? Yeah, we understand the calculation using map. We use the language of MAT. Then I don't need to tell you every time how this compute. I just tell you using equivalent class. As long as these products stay inside the equivalent class of 0, I know what's the product of them. Okay or not? Does it make sense? At least for me, I think this is very down to earth example. If you still cannot understand, I urge you, encourage you, go through this example again and again until you know it. Okay? Any question to understand this example here? Yeah. Yeah, sure. If you pick a different representation, different isomorphism, then you will reshuffle the element. You can also do this. You can also pick a different Y that satisfy the relation. It will still generate S3. Then this is a different isomorphism. Okay. If you pick different generators, then you will form a different isomorphism. Okay. Because your SY is not the same XY as what I compute already. Right. So for example, XY for my case is 2, 3. SY for your case is 1, 3. Okay. So you have a different isomorphism. So yeah. All different. This is a typical example of oh wait. So you are asking like, what is the difference between apple and a fruit? What's the difference between apple and a fruit? Apple is a example of fruit. So I'm just doing another example of a presentation by generators and relation. Does it make sense or not? So I define presentation by generators and relation is very general. Okay. So okay, I think you are confused here. So what should I write here? So I should write this presentation as G1, G2 up to Gn generated by R1, R2 up to Rn. So what are these G1, Gn here? I should add here. So these generators are G1, G2 up to Gn. And then what's the relation here? So these are the word R1, R2 up to Rn. Is it better if I write this? That's better. Okay. All right. So S3 is just a different example of presentation by generators and relation, where I pick G1, G2 as SY, and then my R1, R2, R3 are these words. X squared, Y cubed, and then YX, YX. Make sense? Yeah. Yeah, very good question. So far, any question? No? Any more? Any more question? Session got more question? No more? Okay, so for the plan until final, right? I think we will test until ring, okay? And I tell you details what is, I mean, the detail of the final score, but the endpoint is ring, okay? And if we have more times, I guess maybe just last week or last lecture, then we will briefly go into modules, okay? Yeah. Modules. But the endpoint is ring for the final test, okay? We have to finish rings before week 15. And then if we have extra time, we will cover a little bit on modules. It's a very important objects in the maths. Yeah. Okay, so this is the plan to finish the semester. Okay. If no question, do you want to take a break or you want to discuss the assignment first or come back after break? Do you spread first? Okay, let's spread until 10, 11, and then we will discuss the assignment in the second hour.
是这样，one cycle 全部是2 cycle 全部是 N， 这样的意思你去做因为你这边是选一个嘛。
不能啊，你这个是一个 element 一个 word 罢了，你不能够选一堆，你就选一个吧。所以你每选一个组合，
那就不一样的一个，
就是不一样的还是什么别的？
可是就是这样子每一个，你这6种，6种不一样还是什么
？Yeah，
OK，
哎，没有6种哎，几种呢？
没有3
，actually 有6种，有6种
啊，对6种啊，
对6种。
是你这一边有一个 normal 的那个 conjugation， 但是我们上一个作业有，
哎有 actually， 但是你们就是 hide 在后面哦，你们可能没有发现到，
你没有拿出来啊，
没有拿出来的意思，
你没有抓出来，
没有好抓，就是它是对的，只是你要知道里面发生什么事情。
所以我们其实不用特地拿出来，就是讲它在里面的。因为我们可以就是如果我们要 tag 的话，就是拿出来。
因为你就说 equal 嘛 ，equal 的时候 conjugate 的东西不会变，它 conjugate 在旁边，你中间一直变的话，conjugate 的东西也在里面。呀，可能你没有看到后面在做什么吧？它的，你 formally 你可以 try and show 啊。呀，他们 define 的 normal subgroup 是一样。
其实为什么我们这里不能这样，或者我们这里不能确定这个 relation 它的 conjugate 过后，它是整个可能是吗？
就是我不知道这个 normal subgroup 是不是可能。
对，就是你把它的 relation 3个 relation conjugate 到完了，真的你不确定它是可能。
哦，你讲这个，
没有，这个是已经确定了嘛？这个我们已经 intuition 讲它就是它的可能了。可是
没有 intuition，可以 argue 就是说这2个东西什么时候被送去 identity？它一定本身是什么时候被送去 identity， 还有是他们配下一起的时候什么时候被送去 identity。然后这个是最 simple 的 case，y 乘 x， 所以就没有了，就没有其他的可能性。
这样的话，这种东西就是那种在我们不知道它是不是可能的情况下，就是那种它的整个把它的整个 relation conjugate 起来。假如讲 more general case， 可能就是讲它的全部 relation， 你把它 conjugate 到完了，然后它未必是它未必是它的可能来的，就可能它还有其他的顾虑呢，是这个意思。
没有顾虑是在你拿完了这种基本的情况啊，顾虑只有有没有比这3个再多的问。
对
conjugation 那个是自然的，
就是
顾虑是在
有没有更多的可能性让它evaluate 的 E， 是那种
顾虑，这是在这种 basic 的
就是不同的斗法，其他斗法让它变成 E，
但是最 basic 的斗法就是 yx
其实这个3个已经斗完了，其实已经
或者你要斗的话就斗 xy。有啦，有几个斗法你要 consider 啦 actually， 因为你看你有 basic word e x y 跟 y square 嘛， 所以这几个的组装方式你要组装一下，
嗯，
你全部都要 reduce 去 y(x) 等于 xy square，这样你就解决。你最基本的是 x、y 跟 y square 这四个组合，组合完过后，你要看到是你全部都可以 reduce 成 y(x) xy square。你 check 的那个是要 check 在 S 上，就是比如说这个，如果你选这个 isomorphism 的话，你要告诉我12123 132，随便乘它什么时候回去 identity。然后你如果能够把它 reduce 成最后一个，这样最后一个就是你剩下来的
就是
relation。
把 x 跟 y 把 x 跟 y 他们就是分几个 case 就可以弄得到，
分几个 case
就把 x y combine 就是它的不同 combine 成不同的 basic case 就能看到。
basic case 不是你要选那个 non-trivial 的 concept。non-trivial 吗？x y 跟 y square 嘛，因为你 x square 了又回去 identity 的 equivalent class，y cube 了又回去 identity，所以你只有 x y 跟 y square 这三个 non-trivial 的东西，然后这三个东西互相乘，什么时候它会回去 identity？互乘，因为你知道 x 乘 x 肯定是回去 identity 嘛，y 乘 y
对
你已经在那边了 y square，y square 乘 y square 又回去 y，所以这几个是
一直重复，
就一直在重复，回去 identity 也只是因为他们的 order，这样的话你就要 consider 不同的组合，x y 啊 y x 啊 x y square 啊 y x y square x 啊 y y 也没有什么好搞了，因为它就是 y cube 了，所以只有 x y y x x y square 跟 y square x 你要解决，然后你可以somehow看到最后一个 relation 就是你要 check 一下 x y 等于什么东西
啊 x y 等于什么东西 ？OK，
然后你把它拆出来了过后，其实是从第三个 deduce 出来。
所以其实如果假如我们用这个根据 process 模式的话process 模式，对，我们已经确定它的可能是这个了。
对，
这个是我们在不确定的情况下，我们就是可以用这个确定可能的情况下，就是不确定它是不是整个可能的情况下，
没有可能的话，你不是没有 isomorphism 吗？你有 homomorphism。
然后就是还要另外证明它是isomorphic，这个意思啊。that means that 就是讲，假如我设这个的话，我就是把它灭过去以后，也把它变成那六个东西嘛，那六个 cosine 嘛，就是要一个，就是把它们写出来讲它是1 to 1的，就它的写法就是用这个东西哦，就是因为它的 cosine 是属于也是那个六个，就是一的 cosine x 的 cosine y 的 cosine y square cosine，它的那个代表啊这里嘛，然后就 map 过去 x 的 image 一的 image y 的 image 这样，就是用这个去解释哦。如果复杂生活费的话，就是要把它组装起来，确定它是可能，这样子直接来的，它是爱什么的没有错。
所以我是说你要讲说那个是你的可能，你要考虑不同的
组合法，
其实也只有4种你要考虑吧，x y y x x square y 跟 y square x。
对，因为不然还变其他东西会变 identity 了已经。
然后我是说这些的组合，这些 relation 就是从 y x 等于 x y square 分出来。你应该也会拿到 x y 等于 y。
那明显它
relation
已经出来了，
对，已经出到完，
就没有其他东西可以来做它 relation 了，就不是
没有 basic 的，
没有其他 basic 东西可以做它 relation，就是讲它的 relation，我可以兜出来整个可能，整个可以兜出来它的 normal circle 就是整个可能。对，就是。
可以再讲一次。
它的可能，讲 prove 它可能，你要 prove 的可能是大概几点？你要 prove 它的可能等于那3个东西的话，你要 make sure 只有这些东西被送去 identity。所以你要 make sure that 在右边什么时候他们 compose 去 identity， 你要 make sure 什么时候他们 compose 去 identity。比如说 S square 会去 identity，YK 会去 identity， 在 S3 的时候。然后你从这边可以看到，我们还有什么东西要 check？ 其实我们要 check 的是 XY、YX、XY square、Y square X 这些东西，他们什么时候 compose 去 identity？ 就是说，就是说你怎样 differentiate？ 你看 ，in principle 啊，我们可以造出额外2个字嘛，YX 跟 Y square X， 但是这2个字不出现在我的 image 里面，为什么？你要解释哦，为什么这些东西不会在 kernel 里面，在 S3 的时候？等一下，你啊 ，OK，时间到了 ，OK。Okay, I have returned you the assignment yesterday night. You could check the Moodle. This time, I think the mark improved, the quality of answering improved, but still, I found some plagiarism. Of course, I think you asked. I think a lot of you asked Jimbo, right? And then you guys repeat his weird writing, actually a bit of mistake in his writing. So that's why I can catch all of you. Make sure when you ask your friend, right, make sure you know what they are doing, and then you write out the idea. Okay, don't just follow, just change notation. You need to go one level up now. Okay, now you know how to change notation. Good. Next, you need to write in your own way. Okay, get the idea right in your own way. Okay or not? I know few of you just change notation, maybe change thus to therefore, and then change symbols, I know. Okay, but next, I want you to learn to translate people ideas. Okay, not copy, understand in your own, and then you write it out. Okay or not? Okay. In case I mark you wrong, you please just let me know. Okay, just talk to me. You can claim mark for me. Don't hate me. Okay. So first question here. Is this the first question? Yeah. So you have a homomorphism from S4 to S3. Okay, find the 6 subgroup of S4 that contain K. There are a few ways you guys answer. Okay, so the first basic way is you just directly find what are the subgroup contains K. But this doesn't really address this question here. This question says what? Determine the 6 subgroup. Meaning what? Only 6 here. There's only 6 here. The is the only one. Okay. Take the apple. Which apple? The apple. That one. Not any apple. Okay. So So you need to answer why there's only 6. First you see this. So these are English sentences that you need to learn. Whenever I said determine the 6, so you need to show why there's only 6. Okay. So what do? So the strategy here is to use correspondence theorem. Okay. Because in S4 there are how many subgroups? There are quite a few subgroups inside there. Okay. But we know that S3 has 6 subgroups. How do we know it? the order of subgroup divide the order of the set. Okay, so what number divides 6? 1, 2, 3, and 6. 1 is the trivial subgroup, 6 is the whole group. So how many order 2, order 3 groups? There's only 6 elements for you to play around. Okay, so order 2 subgroup you have 3, order 3 subgroup you have 1. 1 plus 3 plus 1 plus 1 is 6. Okay, then correspondence theorem tells you that there's a bijection between the subgroup contain K and the image subgroup. So this gives you exactly the 6 subgroup that contains K. Okay. But quite happy is most of you figured out what is this homomorphism. Actually, this homomorphism is kind of hard. Okay, not too hard, but there's some level to understand it because you have to pass through the organization of the set, and then you figure out what's the S3 you get. Okay, yeah. You can read my solution. I haven't posted out, right? Okay, I will post it soon after this lecture. Question 2. Let G be a group that contains the normal subgroup of order 3 and 5, respectively. Prove that G contains an element of order 15. Okay, so one way is you to use the injective product homomorphism that we discussed in class, the proposition, or some of you just figured out what's the element you can pick. Just pick A times B and then argue that AB will give you the order 15. Okay, through the normal will give you the abelian property, the commutative property, and then you use the cyclic order, and then the element AB will give you the element of order 15 in your group. Or more formally, we use this product homomorphism, injective product homomorphism, because you know that the maximum order of product group of cyclic 3 and 5 is the LCM of 3 and 5. This is the exam question. Similar exam question. Okay. Most of you do it okay. Actually, 3 is quite hard for this assignment. Okay, because you need to figure out what's the quotient group. Okay. Quite a few of you managed to stop at finding the coset. Okay, coset representative, which is good, but you don't really explain why these are the coset. Okay, so I took off some mark there. And to be precise, right, if you already reached to a stage that, for example, most of you reach to this state. So let's say B, part B. Okay, so what are the coset here? What are the representative here? You can be written as 1, 0, 0, D times X, okay, for D in 3. So meaning what? When you take 2 coset here, okay, when you take 2 coset here and multiply together, right? So how do you multiply 2 coset here? How do you multiply these 2 coset? Do you remember? AH times BH, what do you get? AH times BH, what do you get? ABH. Why ABH? Because if it's normal, every left coset is the right coset. Okay, using the same representative. So you are actually multiplying the 2 representative here. But when you multiplying the 2 representative here, what actually changed? Only the 4th entry here changed. So meaning what? You are really just multiplying 2 real numbers. In other words, there is a isomorphism to reals. What is the isomorphism? I just take the 4th entry out from the matrix. I just read it. I just read the 4th entry. This is what you do. This is how we understand the multiplication, right? So mathematics is very intuitive. We just use language. And you need to learn the language. The hard part is the language. Okay. Okay, no. So to precisely check the isomorphism, you can check my solution. My solution didn't use first isomorphism theorem. I straight away construct the homomorphism and then show that it is an isomorphism. You can actually use first isomorphism by first constructing the surjective homomorphism, same map, and then show the kernel. So this is the two different way. Okay. So I write it out for you. What's the way? Think about. Yeah. Okay. Okay. Let me summarize for you. So two ways to show G mod S isomorphic to, let's say, G prime. There are two ways here. Okay. So first is the traditional way. So what do I mean by traditional way? Use the definition of isomorphism. Okay. So when you say that two groups are isomorphic, right? So you need to create a homomorphism. Okay, phi. Okay. So first check P is of course well defined first and homomorphism. B, you check P is both injective and surjective. Cannot make sense? Okay. In this way, you have a isomorphism. Okay, two, we can use first isomorphism theorem. First isomorphism. Okay, how to use first isomorphism theorem? So you need to build a surjective map from G to G prime. Okay, here homos. And then, so first check P is so it's homomorphism. B, you need to check P is surjective. Then how to apply first isomorphism? How to apply? How to apply? You need to check that the kernel of phi is exactly S. And then the isomorphism pop up. Actually, you know what's the isomorphism? It is also given by the first isomorphism theorem. What's this special map here? Remind you again. This is sending the coset to its representative. This is what we did just now, free group stuff. It's exactly the same. Okay, so this is a different way to show that quotient group is isomorphic to another group. Does it make sense? Okay. Yeah, so the difference is where? So the difference really lies in this injective part. One of them you need to show injective, the other you need to check the kernel. Okay, and then the first isomorphism will send you the isomorphism that you need to give you the isomorphism you need. Does it make sense? Okay. Yeah. For question? not, let's go on. I think question 4 is quite easy. Most of you managed to do it, but some of you, I think, skip some step and then maybe use the wrong step, but give you the right answer. I just penalize a bit. So through the discussion just now, right, Ming Xiu has some doubt on the validity of writing this equality here, correct? Can we just replace this relation like this? What are we actually doing? We are actually changing the normal subgroup that portion by the presentation generators and relation. When you change this relation, you are actually changing the normal subgroup. But the claim here is the normal subgroup are all the same. Are all the same. Okay. So this is the remark, extra remark I want to make for this question here. Okay. Although we are changing the word here, okay, although we are changing the relation, but the normal subgroup that we quotient now doesn't change. I mean, they are equivalent. Okay, they are equivalent. Yeah, they are equivalent. Okay. Sometimes equivalent, sometimes equal. Question? No, you believe me. Okay, any question on this assignment? Any question or not? On these assignments? Yes. Why isomorphism Z cross Z? Then you need to form the surjection. Okay, you need to find the surjection. So you need to send B to where? Send C to where? Yeah, where do you need to send this number to? Where do you need to send B and C to see this isomorphism here? Any idea? Where do you need to send B and C to?
So
Yes.
Z is Z plus Z multiplication.
When is that a group? Right. So what? So if you want to ask about isomorphism, right, you need to ask about what's the surjection you want to make. So what's the surjection you want to make to Z cross Z? You need to, by mapping property of free group, you need to tell me where's the generators going. So B and C should go where? Yes, 1, 0 and 0, 1. And this is a surjective map because Z cross Z is generated by these two elements. And then what's the relation need to be satisfied by these two elements here? B and C has infinite order. Okay. But one thing you know about this group is this group mu. 1, 0 plus 0, 1 is equivalent to 0, 1 plus 1, 0. And all the conjugation. Okay. This is not a field, right? This is a group. Is this surjective on R cross R or not? Can you get 0.2 times 0.2 here? Can you find the pre-mesh of 0.2 cross 0.2? Can you find the pre-mesh or not? You can have a map into here, but any pre-mesh, is it surjective on R cross R? How do we get these other number out? We obtain by taking the power of B. Power of B are naturally live-in integer. Why there's a negative integer? Because we consider the inverses. There's no 0.2 power of A, or B or C. Make sense or not? So for example, what's the pre-mesh of 2, 2? Okay. What's the pre-mesh of 2, 2? B squared times C squared. Why? Because if I say this is phi of B squared, C squared is what? It's defined naturally extended to be phi B squared times phi C squared. Okay, but this multiplication here in Z is just addition. Okay, and then what is phi B squared? Also extend naturally. So it's phi B times phi B. So I just talk about generators. So I just define my map on generators is enough. And it's like the vector space. You just define linear transformation on your basis because you can use the linearity of your transformation to split your element into linear transformation. So this is what? 1, 0 plus 1, 0 plus 0, 1 plus 0, 1, which is 2, 2. Okay? Is it okay? Yeah. Okay. So there's some few of you. No, please. If you have difficulty in your assignment, for example, with Zhe and Raylan, right? Please come and talk to me. Ask for help. Okay, don't be shy to ask for help. And then you are allowed to find external material. So make sure the answer is correct before you write down, because otherwise you will be very wasteful of the marks. And a large portion of this assessment is depend on assignment. So if you can pass your assignment, mostly you are safe. So if you cannot pass your assignment, then it is almost very hard to pass your test, right? Because if you don't do your assignment well, meaning you don't understand the content, then probably you cannot do much in your test. So assignment is a very important assessment in the mathematics course. Okay, and then this is the chance you can get 100 score in assessment because you have times as resources to get it. Okay, don't just use your own understanding. This is not the point of this assignment. If I want to test you, I will do a quiz. You cannot check. I give you limit time and then you do whatever you can. But this is an assignment. So please differentiate between assignments, quiz, test, and so on. Okay. Assignment is not a quiz. It's assignment. Okay. And then some of you have a great improvement. Actually, in general, your class improved in terms of solution quality, not accuracy, but quality. You know what you are doing now. And actually, I think Ying Ying, Zheng Chen, I think Zhe Xuan also did quite good this time. And then I actually have a list, but unfortunately, there's no Seng, Cloud Seng here, so I'm not sure the file is still old. Quite few of you improved, and There are 3 high scorer here. Who is the 3? Ying is one of them. Ziqian is one of them. So they got score 60. And then Kyron is one of them. Kyron finally make to the top in my class. Did you do it? Did you do it differently this time or not? Did you treat it differently this time or the same how you do the previous one? The same, huh? Okay. Because what I can see from a previous assignment is like you always have some concept missing. But this time around, you managed to put all the things together. You managed to address all the technicality, which is good. Okay or not? Yeah. Right. Okay. So let's return to our ring. Okay, let's return to our ring. So maybe we leave some ring exercise to next time, next Thursday, and then we go into the main topic first. Pick up where we stopped last time. So let's restart from a ring homomorphism. Okay, so what's a ring homomorphism? Okay, so a ring homomorphism, obviously from the word, it is a map between rings. Okay, a map between 2 rings. It's a map. So it is a homomorphism, right? So it has to respect the structure. So how many structure in a ring? How many structure in ring? What I mean by structure. Okay, so what's the definition of ring? What's the difference between rings and groups? The LLC, right? So in rings, how many LLC you have? 2. You have 2 LLC, right? So one of them is addition. The other one is multiplication. Okay, we call it a name. Like Wayne said, we can call LLC A, LLC B is okay. As long as they satisfy the right equation. Okay. So what are the ring structure you need to respect? So for all element A, B in R, you need to make sure that phi A plus B is equal to phi A plus phi B. Okay, so this is really similar to group because ring is a group. In particular, is a abelian group. Okay, and then phi AB have to be equal to phi A times phi B. Okay, so for our definition of ring, we are commutative. Our multiplication are considered commutative. If in other code, you will see that these are the commutative rings. Okay. So when I say about non-commutative ring, meaning my multiplication is not commutative. But addition is always an abelian group. Next, we need to impose an extra condition that sends the the multiplicative identity to the multiplicative identity, where 1 is the multiplicative identity. Okay. Phi sends 0 to 0 is a result of group homomorphism, but ring homomorphism won't give you multiplicative identity gets sent to multiplicative identity. So you need to impose it. Okay, you need to impose it. So actually, there's a side question asked by Wayne. Right. So Wayne asks, why if you take the additive identity 0, okay, 0 times all the A in your ring is 0. Have you guys ever proved this or not? in your vector space. Ming-Xiu say got or? Zi-Qian also got or? Wine forgot or? How to prove this? So there is some B in R such that B plus minus B. So okay, equals 0 first, right? Implies B plus minus B times A equals to what? Then this part you need to use your distributive law. Alright, so here distributive law become important. You need to split it. BA plus minus BA. Okay. But of course, you need to show that minus B times A is equal to minus of BA. You need to prove this anyway. So why is it true? Then from here, you will get 0. Okay. Yeah. So this is very similar proof when you prove this property from your vector space. Okay, so let's look at some example of homomorphism. So last time we discussed that we have a homomorphism from Z to FP. Okay, I want you to get familiar with this notation here. FP, what is FP? It's really just ZP. Or you think of it as Z mod PZ, okay? Where P is prime here. Okay. Last time we discussed about this. So what's this map here? How do I define this map? I need to define on my generators. Okay, Z is an infinite cyclic group of 1. So I just tell you where 1 have to go. Okay, 1 have to go to 1 mod P. And then this will determine all where the integer should go. 2. This is a very important homomorphism that you need to take note here. This is a evaluation real polynomial. Okay. At A. Okay. So what does it mean? So you have a polynomial, I evaluate at x equals to a. Okay, so we see this as a map. Now, previously you just substitute. Want to check at the point x equals 0, I substitute x equals 0. Now, you see it as a map, as a homomorphism. Okay, similar story as the free group just now. You just compute the product, but collectively we form a map. Okay, so this is a homomorphism. So substitution is just a map from the polynomial ring to the scalar. Okay, so if I take any polynomial in X, I just go and evaluate it. This is a homomorphism. So you need to check what? You need to check that this map respects the ring structure. Okay, if I give you addition of 2 polynomial, okay, if I give you addition of 2 polynomial, is it true that this is equals to A px plus q a qx? Okay, or this is just pa plus qa? You need to check this. Okay, so you need to check. And then what's the other thing you need to check? You need to check that a px qx is it equals to pa times qa? Okay, you need to check this. What's the third thing you need to check? You need to check that a of the one polynomial, this is the px, the constant one polynomial, is it equals to p evaluated at a? Is it equals to p evaluated at a? So there's 2 different things here. This is a real number. The other one is a constant one polynomial. Okay or not? Okay. If you cannot see, you can request. I can zoom for you. And if you're confused, you should ask. Okay. And there's one very interesting evaluation. Okay, so we can instead of evaluate at the real number, so this is actually real number, we can do some evaluation at complex number. So we will have a map from the polynomial ring over R to C. Okay, we evaluate Px, and then this value here will live in complex. Okay, so that's why we don't really care about the polynomial R. I mean, don't care about we take this polynomial as a formal polynomial instead of function, because we can evaluate at any rings we like. Okay? Any rings we like, as long as the value makes sense. Okay, next. So what's a ring? What's a ring isomorphism? Okay, can you guess what's a ring isomorphism? It is just a bijective ring homomorphism. Okay, it's just a bijective ring homomorphism. So once we have, if we have an isomorphism from R to R prime, okay, among two rings, then the two rings are said to be isomorphic. Okay. If the two rings are isomorphic, we will denote as denoted by R isomorphic to R prime. Okay. And then one thing to note here, you can consider a zero map between R. Do you think that this is a ring homomorphism or not? Is this a ring homomorphism? Why not? What is zero?
The ring only consists of
Say again. Which ring? There are two rings here. Yes. Okay. So to satisfy a ring homomorphism, you need to sense the multiplicative identity to multiplicative identity. Okay. But zero map sense multiplicative identity to where? No, zero map. To additive identity, correct. Okay. So this is not a ring homomorphism unless your core domain is just a zero ring. Okay, where 1 equals to 0. Cannot count. Any question or not before leaving? Any question before leaving? Okay, before leaving, right, I want to make some announcement here. So this semester, I also teaching the calculus 2 is the same version you guys have last time. So they will be having a presentation next Friday. So you guys are welcome to come and ask question. Okay, most importantly. So the time is 6 to 8 Friday. The venue is A3618. A3 library block. You need to use the admin list to go up. 618. I will make an announcement again. Okay? Yeah. Of course. A3618 is a. And then when the time comes near, I will let you see all the topics. if you are interested. Maybe some of them are repeating what you guys did, so you should be more experienced than them, I guess. Okay. Yeah, if no question, we will see you next time. Hey, Tingy, before you leave, can you see me for a while? Yeah. Wait, một điểm mình sẽ okay. Mình send me. Em bố here, right? Em bố. You see em bố here? He's sick, ah. Hey, be careful, ah. COVID is coming again, ah. Please take care, ah. Now, most of you also sick, ah. So please careful, ah. The news already out. COVID is coming, okay? Please take care of yourself. Near here or not? sorry. sorry. Izhou here, right? Izhou. Okay. Okay. Hi, Jingxi.
这个 identity 我看一下啊 ZN 被 evaluate 去 identity 啊，被看成